Okay, let's begin. So, last time we spoke about linear inequalities and how to find their solution, at least by graphing. But of course that was too easy, so let's go a little bit further. Now we're going to talk about systems of linear inequalities. Let's actually do a lot of these guys all at once, because why not? So this is several linear inequalities. Considered together. The solution to the system, if it exists, is the intersection of all of the solution regions of the inequalities in the system. And this region is called the feasible region. So you take a bunch of linear inequalities, you know how to find the solutions for each. Find the space where all those solutions overlap, and obtain what is called a feasible region. And that region is what solves the system, in the sense that every coordinate in that space, once you plug it into any of the linear inequalities, they'll all be true at the same time. There are many cases where this will be very convenient for us to do, to be able to find, and I'm going to actually probably just jump into some examples right away. So, process here. Sketch each inequality with its solution to the same pair of axes. And move it up. So, because I already showed you how to do this for individuals, I probably want you guys to start off trying to do it for a system. So just do what I showed you last time. Just do it all for each thing in this system, one at a time. Just do it on the same pair of axes. So let's jump to the I think I'll do the first two, because they're the easiest, and then I'll have you guys try the other ones. So, here's one. Solve the following systems. X plus y less than 2, x greater than or equal to 0, y greater than or equal to 0. Keep things very similar here, but there's something I also want to introduce to you that will be made evident by these examples. So very similar, I just changed the inequality sign from one to the other. So let me get this one out of the way so you can see what's required here, and then I'll have you do some. Okay, so let's go with A. So we're going to draw our axes, and I'm going to start sketching this line. Now, how do we sketch that line? Quickest way, go. What do I do? Sketch the line. Find the intercepts. How do I find them? Plug in zeros for the x and y respectively and plot the other guy. So if I plug in y equals 0, I get x equals 2. So that's going to be here. If I plug in x equals 0, I get y also equals 2. That's going to be here. So I obtain 2 points. Once you have 2 points, that's enough to sketch a line. So that should be a straight line. This is x plus y equals 2. Here, though, I want it to be a strict inequality, so this should actually be a broken line. So that's one of them. Then x equals 0, well, that's just the y-axis, right? So it's right on top of the y-axis here. That's another one. And y equals 0 is the x-axis. So that's 0. Y equals 0 and x equals 0. And now I can go and shade the solution region. So I want this guy to be less than 2. If I solve for y, I realize that y is less than something, so I want to the bottom. Another way you can realize that where it solves this one is to plug in a coordinate, as we decided before. If I plug in the origin into here, I get 0 is less than 2, which is true. Either way, I realize that below this dotted line is the solution region for that dotted line. Now, I want x to be greater than or equal to 0, which means that everything that's above to the right of x equals 0 is going to be a solution region for this line. Then I want the y to be greater than or equal to 0. This is y equals 0. This means I want all y values above that line. And as you can see, there's one region in which all of these overlap. And that is our feasible region here. So that triangle is the feasible region for this situation, right? Pretty much I did what I did for each line one at a time, find where the overlaps are. Now, some people might get a little bit confused or just not like having to shade everything. You have markings all everywhere. So you do have some other options here. Take whichever one you like. I'll just show you a couple options that you have. So you have this guy for 2 and 2. Again, I forgot to. That, we're going to have that, and we're going to have that. Sometimes what you can do is you can use arrows to indicate the solution. In that sense, we know that the solution for this line was below, so you can just draw a couple arrows on this saying, okay, I want below this, I want above this, and I want to the right of this. Right? So you kind of realize within here, you have all these arrows pointing at each other, and so you can figure out that way that the solution region is this triangle. Either way is fine, just be aware that what you're looking for is the overlap of all the solution regions. And this region here is called the feasible region. Now, that that's A. Any questions on how I did that? Yeah.
Do we need to demonstrate like how you get the feasible region, or do we just keep it?
No, you should just be able to draw this picture. Just make sure you shape the right region. And we'll do a lot more examples where we're going to see how to figure out what that region is. But yeah, that is A. In terms of demonstrating how to do it, just draw it. I'm not going to. You don't have to explain how you're drawing it, but that's the idea. So you solve a bunch of them all at once, find the overlap. Now, I want to make a distinction between the feasible region that we saw here and the feasible region that results from me just turning this inequality sign around. So this is B. For the most part, the picture is going to be the same. I tell my other class, there's this guy on YouTube who also records his lectures, and he's really good at drawing broken lines. He can do it like, he just lets it, the chalk, there's a certain angle he holds the chalk, but when he does this, it becomes broken. And I've been like doing this all day on a board, and I can't get it, I don't know how he does it. So I either have to do this thing or just kind of erase it afterwards. We'll survive. Okay, so we have this, and now I'm looking at B. So what I realize is that if I were to solve for y, I would get greater than 2 minus x, which means I actually want above this line. Okay. So I definitely want to go that way. Also, for x greater than or equal to 0 and y greater than or equal to 0, I know I want to be to the right of this and on top of that. And you'd realize that the feasible region here is a very different one. You realize that it's that whole region there. So by flipping an inequality, I can go from a situation like this to that, and so it's going to be very important that you read the direction in which the inequalities are turned very carefully. This also brings up another definition. The idea of bounded versus unbounded regions. So this is bounded. Basically means region can be contained. Inside a circle of finite radius. So you can imagine I could conceive of a random circle, let's say centered at the origin with radius 3, and that circle will completely encapsulate this region. This is a bounded region. So A above is a bounded region. Unbounded means you can't do that. So B above is unbounded. So you can start it, make the center of a circle the origin, for example, and no matter what size I open the radius, I'll never be able to encapsulate the entire shaded region. So this is an unbounded region, this is a bounded region. In some cases they behave differently, but we'll get to that when we actually start talking. Another thing this brings up is the idea of corner points. So here, also the intersection of any two inequality lines of the feasible region. If it is on the boundary. So, for example, on A, this line intersects that line. This is called a corner point. And these two lines intersect. This is called a corner point. These two lines intersect. That is called a corner point. So this feasible region, this region has 3 corner points. So look on the boundary of the feasible region and find where on that boundary do we have the intersection of any 2 or more. You could have 2 or more. But once there are 2 things crossing on the boundary, you can locate that as a corner point. And these points are going to be very important to the kind of problems that we want to solve. Not sure if I'll get into those, but that's the idea. That's what we call some things. That's kind of how you do it. So now, try these. Again, I'm going to give you several where I just make some slight tweaks, and I just want you to figure out where the answer actually happens. So look at this. That's the first one. Start drawing that one. I'm going to make minor tweaks to this, so if you figure that one out, the others should be a lot easier. Bunch of combinations there, just make sure less than, greater than, less than greater. Once you finish drawing the picture, say which are bounded and unbounded. I'll give you about 4 more minutes to wrap that up. do this. A. Slide plane. Alright, what does this guy look like? Tell me 2 points he passes through.
On the y-axis, it passes through 5 and 4. Or no, that one.
5 and 6.
Yeah, so you plug in x equals 0, you get y equals 4. And you plug in y equals 0, you get x equals 6. So that line is like that. Since we're doing several, let me just label this one, x plus 3y equals 12. And now for this one, if I plug in x equals 0 and y equals 0, I get 5 each time. So there's going to be a 5 here and say here. And I want to connect those two. We also have x equals 0 and y equals 0. This axis here. This axis is here. And also, got the feeling that this is going to be important eventually. So how do we actually find that coordinate? Alright, so for blue dot, you're just going to solve the system of equations. Okay, so 1, 1, 5, 2, 3, 12. You take row 2 minus 2, row 1. This minus 2 times that, this minus 2 times that, this minus 2 times that. I get y must equal to 2. Then, since x plus y equals 5, this must mean x equals 3. So this is the coordinate 3, 2. Now, this actually splits space into a lot of regions here. Let's just name some of them. Call this region 1, call this region 2, call this region 3, 4, 5, 6, 7, 8, 9. So for A, where is the solution region? Yeah, region 5, right here. And you can see, does that help? Notice that if I were to solve for y in both of these, I would get y is less than something. So I want to be below this line and below that line at the same time. Here I'm below that line, but not this one. Here I'm below that line, but not this one. So here I'm below both. At the same time, I want to be to the right of this line and above this line. That's going to be your solution region. It is bounded. So that should be what your A looks like. Now, as for B, so this says here, I want to be above both of those lines, and to the right of the y-axis, to the above the x-axis. So what's the solution region now? 1 becomes the solution region in the second situation. One thing I want you to appreciate, though, is that in the first situation, the corner points would have been here, 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 and here. There are 4 of them. In this situation, the corner points are this one, that one, and that one, right? So you only care about the intersections that are surrounding your feasible region. This one, and this one, and this one, I don't happen to care about at the moment. This one is bounded or unbounded. That was B. C, we had, let's see, less than the 12, but bigger than the 5. Where's this? Solution region here.
About 6.
As in here.
Yeah.
You can check We are above this guy, but below that guy. We're located to the right of this and above that. So yeah, that looks fine. This one has 3 corner points. These will be points of interest later on. And that will be the solution for C. If you did D, it's going to be the same picture. Greater than here, less than there. And this, that. Solution region here. 2, 2. That is below this line, above that line, to the right and above that. So yeah, 2 would be the solution region for D. As you can see, this is a bounded region. So that's where your shading should have happened for D. For E, kept the same thing as D, but we removed the last 2. What results when I do that? Huh? It expands to cover region 3 as well. So, and just keep going, because now it doesn't have to stop at the y-axis. Keeps going back. Bounded or unbounded? Unbounded. Now, bounded or unbounded is important because there are certain times when a certain kind of solution we're looking for might not exist for unbounded regions, but for bounded regions, the solution always exists. Yeah, that's a system of inequalities. How you sketch them and find the so-called feasible regions. That was clear. So these are just some preliminary, and of course the idea is if you ever need to find an intersection point, if it's not obvious from the graph, like I mean this intersection point is obviously 0, 5. Any other one, you just set up a system of equations, solve for the point. But now you should know how to sketch them, find the feasible region, know how to find the corner points. That are prerequisite skills to the things that we are going to be doing, which I don't know how far we'll get into it at this point, but it's going to be linear programming. Which is unbelievably useful in a business context. A lot of the models that you'll be working with will have a linear programming background. So the real goal here is an idea called optimization. So there's a very important word called optimization, and loosely speaking, this is making some situation as good as it can be within some constraints. The process of doing that is called optimization. You want to optimize the situation means you want to obtain the best possible scenario given certain restrictions you might currently have. Now, mathematically, this often involves maximizing, meaning finding the largest value, or minimizing, finding the smallest value, some function. There are many optimization techniques, many different kind of models and approaches that you can use to approach optimization. In the next class, Calculus 1, 1109, you will learn how to use calculus to approach the optimization situation, where calculus can approach the optimization situation. Here we're not going to use calculus though, we're going to use these pictures that I've been drawing to actually figure this out. Which sometimes is all you would need. So if you have only lines being present, you don't need calculus, you can use linear programming. In fact, what linear programming is, so you have some linear function that you really care about, and in particular you care about finding where is that linear function at its highest value or its lowest value in the presence of linear inequality constraints. Function we use to optimize is called it's called the objective function. You'll use the same language in calculus, by the way. You'll learn about the objective equation. So you have some objective function. It is a linear function. It is very important for you to figure out when this function is a maximum or minimum in a certain particular situation given to you by linear constraints. The process of doing that is called linear programming. There are many ways that we can do linear programming. We'll focus on the graphical approach. The simplest method is a computational approach that's also really popular, but we'll focus on the graphical approach to linear programming. So that's it. So you could be in a situation where a very simple thing can be in a business. Your profit equation is often going to be a linear equation. It's going to be your revenue minus the cost. So you have these fixed costs, or they might also change linearly, like rent and what you have to pay your employees and what you have to pay in insurance and what you have to pay all these other things. And then you have revenue, which is the number of products times the price you're selling those products for. And then you can start to think, well, I'm only open for 8 hours a day. I can only make so many products per day. If I really push the overtime, I can get up to this products, but I'll never be able to make more than that. I have this many salaries to pay, blah, blah, blah. How do I maximize profit? Right? Given that I have all these restrictions, all these things I have to do with the cash flow that I have, how can I make this particular thing over here as big as it can possibly be? Or how can I minimize cost, right? These are all situations that you would be very interested in. So let's actually jump into an example. We're going to make it through this example. Let's try. Now, it's going to be out of context. We're going to just look at the basic mathematical foundation. suppose f of xy is x plus 2y. This is a linear function. Maximize f of x given that. Okay, so for some reason this is going to be some function you care about, and we'll talk about how you can develop this function if it's not given to you. Given that the following are true, 2x plus y must be less than or equal to 22, your x plus y must be less than or equal to 13, your 2x plus 5y must be less than or equal to 50, x must be greater than or equal to 0, and your y must be greater than or equal to 0. So let's just pretend, for whatever reason, the situation you're in requires these things to all happen. However, this is something you care about a lot, and you want that to be as large as it can possibly be, given that you have these restrictions on the variables. How would you actually go about doing that? Well, step one, find the feasible region. Space to do that here. I don't know. Let's do this quickly together. So the feasible region is just us solving this system of inequalities. Here, if I plug in x equals 0, I get y equals 22. If I plug in y equals 0, I get x equals 11. So I have a line of these. So this is 2x plus y equals 22. Then I will have x and y equals 13 respectively. Let's call that 13. Let's put 13 over here. So I have that. I need 2x plus 5y equals 50. So my x is going to be 25. Put 25 over here. And my y is going to be 10. Put that over here. So this is not drawn to scale. I'm not exactly sure if it should go over or under. How would I figure out where it should go? Well, what I could do is I could first find this point, and then find where that line would intersect with the other lines, and I can tell if it should intersect before the intersection here or after the intersection here. I'll actually know how to sketch it. So how would I do that? Find the intersection of the first two. So if I have 1, 1, 13, 2, 1, 22, what I can do is row 2 minus row 1 minus 2 row 2. Two row 1 minus row 2. 2 minus 2, 0. 2 minus 1, 1. 2 times this is 26, minus that, 4. So this means my y value is 4. What is my x value? So if I add x plus 4 would equal to 13, so my x must be 9. So I know this situation here is going to happen at 9, 4. So I know this here is where x is 9. Now let's intersect, say, this line with that line. Do that in purple. So 1, 1, 13, 2, 5, 50. 1, 1, 13. Then I can do 2 row 1 minus row 2. 2 times this minus that, 0. 2 times this minus that, minus 3. 2 times this is 26 minus 50. Huh? Negative. So here I have that y is going to be 24 over 3, which is 8. And my x is going to be x plus 8 equals 13. So my x is going to be what? 5, right? So this one actually intersects before. So this one is going to intersect this one over here. 5. So not drawn to scale, obviously, but it's going to come over here and go down there. These should all be straight lines. So yeah, what's our feasible region here?
A little triangle in the middle there.
This guy right here?
Yeah.
That's the feasible region. So whatever solution I want to maximize this function in, it has to happen in this little area right here. And step 1 is to find that area. We'll finish next time. Step 2 is going to be to find the corner point. And we'll finish this up. All right.